Sounds good. Yeah, so my name is Brian. I'm in Minneapolis with Keysight, and I'll go ahead and kick this off. We will be recording this event, so if anyone wants to rewatch it, or if somebody couldn't attend, it'll be available for anyone to see after the fact. On the control panel that you see, I want to call your attention to a couple of tabs. Under materials, there's a few documents you can download, including our Power Handbook. A copy of the slides today will be made available after the webinar as well. So don't worry about taking copious notes. You'll be able to get a copy of the slides. The bottom tab in that control panel is chat. And we're gonna, if you have questions during Alan's presentation, go ahead and enter them into the chat. And then at the end of the webinar, we'll read those questions out one by one and answer them. And then we'll also give you the opportunity to open your audio and ask live questions as well. We do that just because some of the attendees are on a fixed time budget and we want to get through the material first. So anyway, welcome to today's battery test and emulation webinar. And today's event is brought to you in part by Newark, one of our valued distribution partners. Many of the solutions we'll talk about here today are available sometimes in stock at Newark. So yeah, today's seminar all about battery test and emulation. So many devices out there have gone wireless, and for some of those, maybe most of them, battery life is a critical issue in terms of success for the device. So that's what today's webinar is all about. Let's see some logistics. I guess we talked about holding questions till the end or entering them in chat. We'll see. Yeah, we'll send everybody a copy of the slides, and then after Alan gets done with his slides and demonstration, because a lot of this event will be live demonstration, we'll throw a poll up where you can. We're basically taking the temperature, I guess, of the audience in terms of any information they might need afterwards. And then, yeah, I think, at the end of the presentation, when you close your browser out, there will be an evaluation form. We ask that you fill that out if you have time. It's a great way to write free-form feedback or questions, or let us know that you want us to contact you after the fact to talk about your application. So there's 4 of us at the top there, I guess. Alan Wadsworth will be doing most of the presenting here today. And then, yeah, myself and Paul is with our product group that manufactures our power supplies and these battery life emulation products. And then Dave Walter is our distribution manager. He takes care of our distribution partners like Newark and makes sure that they get what they need from us. So yeah, so with that, I'll turn the reins over to Alan Wadsworth, who is a business development manager here at Keysight. He's got some really great slides and demonstration, and then we'll answer questions after his discussion. So Alan, I'll hand it over to you.
Okay. Are you seeing my screen? I'm not.
Yep.
You are?
Yep.
Okay, great. Let me go to full screen mode here then. This thing's jumping all over the place.
Yeah, there, that's nice and good sized as well.
Yeah, hold on here. If I click this. Okay.
And Leslie, have you started the recording?
Yes, I have.
Okay, good. Just wanted to make sure. All right.
Okay. All right. Sorry, I was just fixing things up so I can see my own screen here. I got so much stuff going on. Hi, everybody. Yeah, again, So I'm the business development manager for precision and power products here at Keysight. And of course, today we're going to talk about some new solutions we have for battery test and emulation. So don't worry, I don't have that many slides, but I did want to go over a few things before I get into the demo, because again, I don't really know exactly the level of everybody attending this call. So I just want to make sure that everybody is kind of up to speed on everything. So I'm just going to talk first about battery characterization basics, then talk about a little bit about some of the methods for DCIR battery characterization, which is what we basically are doing. Again, talk about some desired capabilities of battery modeling software. Then again, I want to spend some time, maybe 50-50 probably slides demo, but slides showing our new advanced battery test and emulation software. And then at the end, I'll give you a little summary and some additional resources if you want to learn more about anything I talk about or some of our other products. So again, starting off here, why is battery characterization important? Of course, again, we all want to understand how much energy a battery can store and supply, right? And it's actually not such a simple question. Maybe talk about that more, but we talk about state of charge and how much energy is in a battery, but that really can depend a lot on how you drain the battery, honestly speaking, and the temperature. And there's many different factors that affect how long a battery will actually function in it, for a given device, and lots of different parameters to look at. So and also how you create the model of the battery can also be very important. So we'll talk about that later, but it's not such a simple thing really to actually understand how much lifetime do I get out of a battery. Because again, you want to validate the battery performance under a lot of times specific conditions and operating modes. And again, as I said, temperature is important. Also the profile, how exactly are you drawing current? I mean, you get different performance depending on whether maybe you have a constant current draw or you have some kind of variable current draw. There's also other types of ways of obviously drawing current, constant power, constant resistance, things like that. And in the end, what we really want to do is obviously we want to create a battery model or some kind of battery profile under specific discharge conditions so that we can go back and test it out and see how it actually performs with our device. And again, there's different factors, temperature, load current profiles, things like that affect all this. So again, this is really why we want to characterize batteries and what actually makes it kind of a challenge also. It's not such a simple thing. So again, this is a little bit basic, but I did want to cover it. I just have 2 slides on this. So again, just a quick review, what's a cell and what's a battery. So again, a cell, of course, is basically kind of a fundamental building block. It's based really on the chemistry of the battery. And again, the voltage of the cell is pretty much determined by the chemistry. You can't really alter that. The capacity of a cell, of course, is determined by chemistry and volume. So again, you can increase the capacity of your cell by just making it larger. Again, 18650 lithium batteries are pretty common. Actually, that's what I have for my demo device too. But again, the voltage of a cell, again, as I said, is always the same regardless of the capacity. So again, you have low capacity, high capacity, basically pretty much dependent on the size of the battery to a large extent. Then when you go and look at of course, a battery itself, a battery will consist of 1 or more cells, and sometimes what we call a BMS or battery management system to kind of control things. So again, sometimes it could even have some kind of protection circuit. Sometimes, of course, some batteries have other protection features built in. Typically, lithium-ion batteries have some sort of mechanism. Well, not really. How would I say this? They have some protection built in so that you overcharge them, they don't explode, or at least destructively or explode, things like that. But what you can do, as you can see in the lower left there, is if you want to increase current, you can put cells in parallel. In this case, put six in parallel. Obviously, gives us 6 times current, 6 times power, 6 times capacity. Of course, you can also put cells in series, as shown on the right there. And again, you get same current, but you do get twice the voltage, twice the power, although it doesn't actually increase the capacity. But again, of course, using these different cells, you can build up a battery to kind of whatever you want, as shown like in the bottom right there, if you want to have something you might want to use in a car, electric vehicle, something like that. So I'm going to talk about the kinds of battery models there are, what different kinds. And again, when I'm talking about this, I'm talking about it in terms of the electrical engineering aspect of it, not the electrochemical aspect of it. Again, because that's really what we're concerned with here, right? So there again, there's kind of 6, this is maybe a simplification, but I kind of define this into 6 levels of battery modeling. So again, the very simplest would be simply a fixed voltage source with no resistance at all. And again, I don't know too many people that would use this, but I guess you could say it is the simplest way of, say, modeling a battery. Not very realistic, however. A little more realistic would be something like this, which is basically a Thevenin equivalent circuit, right? So you have a fixed voltage source and a fixed series resistance value that you're using for your battery model. Well, what's the issue with this? The issue is that basically this really isn't true how batteries behave, because it's true at any instant in time you can model a battery like this, but basically we know, or I can show you that as you change the battery, as you drain the battery or charge the battery, the open circuit voltage and the series resistance do change. They're functions of the state of charge. So the next kind of level then of battery modeling after this would be to go to something where you have a voltage, an open circuit voltage, and a series resistance at some value of state of charge. Okay, but maybe not, still maybe fixed, but at least you know what state of charge you measured these at. But again, a better model, and the one actually I'm going to be focusing on really for this presentation, is one where you actually measure the open circuit voltage and the series resistance as a function of the state of charge, which, as shown here, is really, when you're talking about state of charge, it's really a function of how much current you've drawn or put into the battery, if it's a rechargeable battery, over time. So really, it's state of charge as a function of current and time for those 2 particular parameters. So, and now in addition to that, I guess the next level of battery modeling you'd say you could probably go to would be to include temperature as well. In this case, you're kind of getting into almost a 3-dimensional type of model. So you're talking about state of charge, time, and temperature. Now, we actually are not doing that currently on our model, but we are looking at it possibly as something we could add in the future. And then if you want to get even more complicated, I suppose the last level would be to include some additional, for example, RC networks into this model. And that's not something we're actually going to talk about or touch on here, mainly because our models are all based on using a PC, and you can't really model a battery, at least an RC network. The response time of the PC isn't really fast enough to model an RC network. So again, that's not what we're going to be talking about here. But again, that would probably be, if you had certain, in some cases, again, that does give you a little more accurate model of the battery. Okay, whoops, here we go. So there's basically 2 ways you can model batteries. There's the AC resistance and the DC resistance. So we're going to be talking only here about the DC internal resistance measurement method. It's pretty much a pretty common method, basically, to obtain model parameters for a battery. Again, you have to have some sort of a current source or a source, but actually the point is you need a 2-quadrant source, because in order to measure both charging and discharging, you have to obviously have a way of sinking current as well as sourcing current. And the other factor too is that the current source has to be able to supply fairly short current pulses at pre-specified points along the state of charge curve. So let me just emphasize, you can't, the point of this is you can't just use any old 2-quadrant supply necessarily, because it actually has to have very accurate measurement capabilities and very good timing resolution as well. And this is where a lot of measurement equipment actually does kind of fall apart, is that if you want to get, again, if you want to get a really accurate battery model, you have to have some reasonably good equipment to do it. And so it is important to have equipment that can apply these precise pulses and also have very good timing, because remember, you're measuring voltage and current, as I'll show you later. You have to measure voltage and current simultaneously. So you have to get accurate values for both values, basically. And again, this also has to be done over a time period as you're tracking the charge level of the battery. So what is the DCIR method? Okay, so basically what we're doing here as we're we're looking at say the cell volt, whether we're charging or discharging the battery, is that we're actually going to be applying a pulse to charge pulse or a discharge pulse as we're going along, and that's going to of course have some impact on the cell voltage. But again, we're doing this fairly quickly, either 100 milliseconds or less. Normally, actually, we're quite a bit less than that. I'll show you, we're probably 10 milliseconds or something like that on most of the stuff we do. But it has to be fairly quick. And I'll show you the next slide how this works. So if you want to measure a charge pulse, for example, here, what we're doing is we're applying the pulse. And again, we want to have a pretty fast rise time on the pulse. So here we're going from 0 to 1 amp in this example for the charging pulse. And again, that's going to cause a change in the battery voltage. So you're going to have a voltage before the step and after the step. So you get a delta I and a delta V. So, and again, this is the upper one here, the change that you see in the battery is actually the, you get kind of an ohmic response, and you can also get an electrochemical response in the cell. And again, the cell voltage, of course, increases because the cell is being, charged, right? So in any case, we can calculate the series resistance by simple delta V over delta I calculation using this pretty basic formula here. And so it's pretty straightforward how this is done. But again, think about it. You do have to have the measurement equipment that's capable of doing this kind of pulsing and also making the measurements. And as I said, you have to have everything aligned up here to get a good good data. So you have to have the accuracy and the voltage and current measurement sufficiently good to get, otherwise you're just going to get garbage data. And again, similarly, when we're trying to do DCR discharge pulse, basically it's the same kind of process, except in this case, of course, we're doing a negative current, so we're going to be taking current from the battery, and that's going to again cause a decrease, quick decrease. And again, you get an ohmic response, an electrochemical response, and of course, as you're discharging the battery, again, the voltage will slowly decrease over time. And basically, but it's the same concept and the same formula. So again, the same type of procedure as for the charging pulse. So again, what kinds of things do we really want to have in a battery model? So again, we want to basically be able to discharge the battery with realistic current profiles identical to those of the device that it will power. And it's not that you never want to do a simple discharge of the battery, but again, you can find out very quickly as you play around with this or try this out that the data you get for the battery will vary wildly actually with how you discharge the battery. And I played around with that. I mean, whether you discharge the battery with a very large current or a small current obviously does affect actually its capacity, how much amp hours it really seems to contain. And also, but more realistically, most batteries, most devices are changing, especially if you're looking at an IoT device, you're going to see that current draw will change over time. And I'll show you later, we can actually simulate realistic current draws for a variety of different types if you want to, but it's very important because you will get different results for the battery. And again, you want to also, as I said, you want to track and record the open circuit voltage, AOC, and the internal resistance versus the state of charge. So it's very important to keep tracking those and get accurate values for those. And again, we want to have different battery models. So there's you're going to get a different battery model, depending on how you charge it or discharge it. Honestly speaking, so it's not like you just get one battery model for your battery. You have different ones under different conditions. So you probably want to understand all those different conditions, different load profiles. If I drain, say, constant power, if I have constant resistance, and also temperature is another factor. Obviously, you might want to test the battery under different temperature conditions just to see how it behaves. So again, these are all things that are very important to get a realistic battery model to understand how your device is actually going to perform using the battery. Now, just to show you, so actually for our solution I'm going to show you, we actually can support a variety of different types of equipment. Now, I'm actually in the demo, I'm going to be using an N6705 DC power analyzer. Some of you may already have those, may be familiar with it. The N6700 is the one we use more for production test. And again, that would be kind of for the lower power level stuff. So if you wanted to do coin cells or batteries, maybe pouch cells, things like that. But our software actually can also control higher power things as well. So we also have our APS supplies, which can be used to control much higher levels, and also our regenerative power supplies, the RP7900 series, which could even be used, for example, if you wanted to test discharging and charging an electric battery for a electric car or something like that. So it's kind of nice software in the fact that we have this wide spectrum of solutions available that you can use with different types of hardware for different types of applications. And it's, again, the same exact software, just different hardware used. So, and by the way, so we're using, let me point out, for the N6705, we actually support all except this one particular SMU. I can say, why are we using SMUs? Because of course they're two quadrant, and also, but they also have very accurate measurement capabilities. And as I said, it is very important to have accurate measurement capabilities in the hardware that you're using to make the measurement. Otherwise, you just don't get a good battery model. So again, if you get a battery model, then you can also use that model to emulate the battery. But why would you want to do that? Well, for one thing, it can maybe sometimes create a safer test environment than actually using a battery to power your device. It also is basically obviously more repeatable too, because batteries can be a little flaky or variable depending on well, a variety of different factors. So that's a nice thing. I think maybe the most important thing, though, possibly, is the fact that you can immediately duplicate any desired state of charge. And I'll show you in a little bit how that works. But again, you may want to look at how does my device perform if I'm at like 100% or 90% state of charge. Or also, maybe I want to know what happens when I go to 20%, 10% state of charge. Well, that's what we can do with our battery emulation. In fact, any good battery emulator should be able to do that. And then again, that's the real advantage, because you can very quickly do that and see how your device performs. So it also, again, reduces test setup times as well, obviously, because you don't have to switch batteries in and out or anything like that. You just have a piece of equipment set up. You can program exactly the battery conditions you want to emulate and then just look at them. So again, lots of advantages to using a battery emulator instead of an actual battery to drive your device. So how does our battery emulator work? Well, basically what you do is, and I'll show you this and again in the demo, but I kind of wanted to go through the steps so it's a little more, so it's clear when I do the demo. But you load a battery profile into the battery emulator. And again, you can see here that you've got the, open circuit. So here's at the bottom, you got the state of charge starting off at 100, going to 0. You got the open circuit voltage and the series resistance. And basically then you can specify an initial state of, state of charge. In this case, it's 90%. You can also specify, by the way, a cutoff voltage too. So in other words, if I want to start at 90% and I want to simulate the behavior of the battery, well, maybe I want to stop the test when it drops to 3 volts. We can do that in our emulator. So again, that's kind of important. Then basically the emulation or the emulator will go ahead and measure the device charge consumption. And in case you can see in the bottom here, there's a smartphone current during the boot process. But so basically, we're actually measuring the current that is being drawn or from the emulator into the actual device. And then based on the measured discharge, it will modify the battery emulator. Keeps modifying its output to follow the behaviors, just like it actually was a real battery. So in other words, it's just like you're draining a battery, and the state of charge will go down as the test is proceeding. And again, when the battery emulator reaches the actual cutoff condition, it'll stop running. Now, of course, you could have a cutoff condition that's also just reaching a certain state of charge as well, or you could have both specified. So again, behavior is just like a battery. And I think you can see that having the emulator capability is really nice in terms of like simulating how your device will actually perform with a given battery. Oops, there we go. And again, just as I said, for the battery modeling part, we can actually also validate the lifetime battery performance with the emulation. Just like as I said, we have all these different levels of hardware support, so we can go from very small devices like some IoT device, a tracking device, a smartphone, or maybe if you want to get a little higher power, we could go to an e-bike. And as I mentioned before, regenerative power supply, we could do like electric vehicle charging, discharging types of things. So again, the same software works for all these different types of devices. So lots of variety here if you can, in terms of what you're doing. I think most of this audience is probably more interested in the lower power IoT stuff, but I'm not sure because I don't exactly know who's attending. But again, we can control all these different levels of power. Another thing that's kind of important is that we also have different modes supported for the battery. And when you want to simulate battery charging and discharging, now currently, by the way, for the discharge mode, we only support constant current mode, but we actually are working on supporting constant resistance and constant power in the next release of the software. And again, so if you get the software, since it's a subscription-based model, you'd automatically get the next update when that's available. But the reason I'm mentioning this charging mode, CC plus CV, because it's important to understand, because when you're charging a battery, if I say I pick CC mode and I want to charge it with some constant current, as you sort of approach a full charge, as the battery approaches maximum state of charge, the current will start to decrease, right? So you actually can't continue to operate in constant current mode, obviously, as you get to towards the peak state of charge. So it actually has to transition from constant current to constant voltage mode, because again, the voltage will drop. In fact, you normally will set like you can set a limit, like say the current drops within a few milliamps or something to a certain level, like maybe 5 milliamps, then okay, I say I'm fully charged at that point. But maybe I started charging at 200 milliamps. So obviously I've gone from CC to something else, but the software does support that transition. So as you go, as the battery does get charged up, it will transition over from CC to CV mode. And of course, we also can support a CV mode of charge as well. Another thing that the software can do, by the way, so another important feature of batteries is also you want to verify their lifetime performance, right? Which means you want to cycle the battery from charging, discharging. And again, that can get a little tricky sometimes to do on your own. So because you need a lot of different types of hardware, right? Because you need, if you wanted to do this on your own, set it up, you'd need a power supply, an E-load, a data logger, maybe an arbitrary waveform generator. So again, if you tried to do this on your own and set it up, it could be kind of complicated. So the advantage of our solution is all the hardware we have supported, all those different products I showed you earlier, they actually can do all those different functions. So again, instead of having to like cobble together a bunch of hardware and software to do this, especially if you have complicated charging, discharging cycles that you want to simulate, you can actually do this very easily with the solution. So again, you can very easily validate the battery lifetime over many discharge charging cycles without having to write any code. So again, that's another nice feature of the software. It can do the battery cycling for you. All right, so what I'm going to do now is switch over. I'm going to check my time here. Oh, good, halfway. So I'm going to switch over and actually show you the software. And so again, when you first boot up the software, you'll see these different modes. So there's an emulation mode, a profiler mode, a discharge charge mode, and a cycling mode here. And since the most common question we often get is can I control this remotely? I did mention here, yes. By the way, there is an API available for test automation. So if you wanted to say control this in some other language, like I don't know, C#, Python, or something like that, we have APIs that you can use to control the software if you want to automate it. So yes, you can do that. So I know that somebody's going to ask that question. All right, let me let's see here if I can exit out of this. All right, and pull up the software. Excuse me here, go to full mode. Okay. All right, so hopefully everybody can see this now. So again, as I said, there's different modes: emulation, profiler, charge, discharge. Let me start with the profiling mode here. So I actually have a battery hooked up here, so hopefully this will work okay. But you can, again, over here is where you can go in and change the different modes. And actually, let me back up a second. So let me show the instrument connection here. So just
Yes,
to
we
show
have
you
seen
right
this.
now, there's two versions of the software we have. One can control a single instrument, one can control up to 4 instruments. This is the version that can control up to 4 instruments. And right now I've got an N6705C connected up to the to my computer, so I can control it very easily with the software. Again, you could, as I said before, you could have different instruments if you had the APS power supplies or a regenerative power supply. Those are also controllable via the software. So, and again, the N6705C has you can actually put up to 4 SMUs in it, so you could have quite a large number of SMUs if you wanted to, controllable with the software. In any case, so I can set up different modes here. What I want to do, again, I'm going to do profiling, and I can do either charging or discharging functions, of course, in the profiler. Here, of course, I can set up what file name I want to use, the location of the file. Down here, you can see, so in the case of discharging, I can, of course, tell it whether I'm doing a primary, or i.e. non-rechargeable, or a rechargeable battery. Again, currently, we only support the CC discharging mode, but again, future versions of the software will support other version or other modes of discharging, but currently it's just CC mode. Now, this battery, I'm going to show you, I'm going to actually drain it a fairly high current, mainly because it's got a pretty high capacity and to see any change. So I set it up to do 500 milliamps. But there's other ways. So again, constant current may, as I said, may not be the best way to do this. So you may also want to do a dynamic. So we can do that a couple different ways. So if you want to, we actually have the ability to create a waveform, arbitrary waveform. So you can go in here and, for example, there's different, so I could do square wave, ramps, things like that. Here I can go in and set amplitude, frequency, duty cycle of a square wave. And if I want to use that waveform, I can say insert. And if I wanted to then maybe also do like a trapezoid, I could do that. So you can see here that if I wanted to, I could actually use this editor to build up some sort of more complicated waveform. And again, if I wanted to probably more accurately duplicate the current drain on a realistic device under different conditions, I probably would want to do this. But it's up to you. You can. It's an available feature, and it's pretty straightforward, pretty easy to use. Now, in addition to that, you can also, if you've got a recorded waveform, let's see if I can find this. Let's see, here it is. So if you can actually go in and record a waveform. This is really just a CSV file, by the way. It's pretty straightforward to edit these things. But you can actually go in and if you want to measure the current draw on your actual device, you can do that. You could actually use the actual current, the realistic waveform profile of your actual device to drain the battery as you want to go ahead. Anyway, I'm going to go back and use constant current mode. You can set up here the capacity rating of your battery. You can measure the battery voltage if you want to initially. I could do that, I guess, real quick here. So it's going to tell me what the battery voltage it's measuring is. My current pulse width, again, for the DCIR measurement, there's a little bit of rest time, so it'll stop draining the battery, give it about a second before it actually does the pulse. You can set, again, different cutoff conditions. If I want to set it, I can set it, like I say, I can set it to consumed capacity, so this would be theoretically full capacity, or I can set a cutoff voltage as well, as I mentioned, when I want to stop draining the battery. 2-wire, 4-wire, well, you really should only use 4-wire connections for this, otherwise you're not going to get good resistance measurements. In fact, I apologize, my setup's not not so great in a way. I need to fix it. I'm not getting the best 4-wire measurement on my setup, but I didn't have time to fix it up. So I'm getting, I think, a little bit higher resistance than I probably should. But in any case, you set all these parameters up. Let me go ahead, and the battery's hooked up, so I'm going to go ahead and start. And you can see here, it's going to take a second. It's going to do an initial measurement. So again, it's going to do that initial current pulse measurement, and then it's going to start draining the battery at 500 milliamps. So there we go. So up here you can see, so it's starting to drain the battery under the conditions I specified, and it's going to measure. Now I only have 1 point, so I have to wait for it to do the next measurement before you can actually see the graph at the bottom. But in a second you can see. So again, it's just going to go ahead and measure, keep doing this until it reaches its stop condition, essentially. And again, it's measuring currently, so initially it's measuring 89 milliohms resistance. And again, you can see the open circuit voltage it measured is 3.64 something, 3.65. And obviously I'm not going to keep doing this for very long because it's going to take forever. This will actually take hours to drain the battery probably. And this is a fairly, not super high capacity, but these measurements do take a long time, so it's not something you're going to want to. You're probably going to sit and set it up and then walk away, get some coffee, come back later when it's done. But okay, so now it's going to stop. You have a little bit of a rest. Do the next DCIR measurement, and that's really all I wanted to do before I stop this, because I want to go to the bottom here and show the graph. So again, these are just the first couple of points, but again, you can see, so at the bottom here, it'll show you the capacity of the battery. Again, this is auto scaled in both directions, so it hasn't drained very much, but it'll track the open circuit voltage there on the left and the series resistance on the right over time. So again, when you keep doing this, it'll eventually, this is basically how you build up your battery model. So, this is, how it works. Pretty straightforward, pretty simple, pretty easy to use. All right, so I'm going to stop this. Okay. So then this might take me a second here, because what I want to do next is I actually want to go in. Oops, sorry. I'm not going to do the discharge because that's obviously just the inverse of what I just did. I want to actually try to show the emulation here. So what I'm going to try to do is, let's see. Let's see if I can find this one. I think is a good one. So this is a measurement I made on a battery, and I apologize because I think the resistance is high because I had a bad connection, I realized later on. But in any case, it's irrelevant for the purposes of the demo. But you can see here, so this is a model, and while let me try to change this configuration while I'm talking here, because I have to redo some wiring here in order to do this demo. So let me pull this off here. But you can see that I pulled up this this model, and I can okay. So what I'm going to do for the demo, by the way, is I'm going to use my I have an E-load plugged into the or as my second as one of the modules in my whoops, change my connections, and hopefully this is the right cable. Let's see here. I got a lot of cables next to me here. Good. So simplest way to just emulate this is to set up my E-load is either like some sort of constant current, constant resistance mode or something like that, and then I can emulate the battery behavior. So what I'm going to start off by doing is I'm going to set my E-load to draw 500, hopefully. Well, actually, let me try this. I think that's too high. Let me go back in here. I'm going to change this to say 200, whoops. All right, oops. All right, so I should have my E-load set up to do 200 milliamps current draw. I'm going to turn that on. It's going to be on unregulated mode because it's nothing feeding it right now. And then if I start, say start this. Yeah. Okay, so the E-load is drawing 200 milliamps. So you can see at the bottom, basically you're seeing the 200 milliamps going into the electronic load. And then essentially now I'm emulating the battery behavior. So it's just as if I was drawing 200 milliamps from the battery into whatever device I'm going to power. And again, as you can see over time, slowly the battery will also deplete. So basically what you'll see is, so this state of charge point here, which started at 50%, now it's already gone down a little bit. It's going to be slowly moving over there to the right as we go along here. But again, we can. This is basically how you would then use the model. So the model I'm showing here is one that I created by just doing the charging discharging of the battery, as I showed you in the modeling part earlier. You can use it in the battery emulation part here, and basically use it to power your device. So again, you can simulate the battery behavior without actually having to use a battery. And again, then as I said, the nice thing is you can set this to whatever point in the curve you want to, whatever value of state of charge you want to look at. And so it's much more convenient for in terms of like doing the actual testing of the battery. All right, so I'm gonna maybe stop this for now. And it's hard to know because I can't see the thing. I'm sure there's probably a lot of questions going on. So again, there's so as I showed you, there's the profiling and the emulation are probably, maybe two of the more important areas, certain things we can do. We can also, again, do, I'm sorry, I did this one already. Whoops. And then we have the battery, profiling. We can load the profile. There's the battery cycling as well. If you wanted to do battery cycling, again, we can set up and do different types of cycling, different types of sequencing. So overall, this is a pretty complete way of doing battery test and battery emulation. So at this point, let me see here. It's about 10:42. Maybe we should open it up to questions and see, because I need to look here and see if we have a lot of questions. I don't know, Paul, do we have a lot of questions that are coming up that we could answer, or that people have questions on the demo?
There's a few questions on the chat right now.
I see.
While you're doing that, I'm just going to launch a poll just to see if there's some information that people might be looking for. So I'm just going to put that up for about a couple seconds.
Okay. Whoops.
But you can be talking over it. It'll come back to you, Alan.
Yeah, and maybe let me read off a couple of the questions that came in via chat. I think Paul answered one-on-one, but maybe the rest of the group would be interested in these. Do you ever have customers that want to use electrochemical model to generate the parameters for any of your electrical or electrothermal modules, i.e. before test data is available? Paul, did you want to provide an answer to the group on that one?
Sure. So basically, any battery model could be loaded into our software when you're emulating. The model doesn't matter what type of chemistry, what type of battery is being used. It's simply if the battery model content contains the open circuit voltage, the state of charge, and the series resistance, as the battery is either being depleted or being charged, for example, we could emulate. So you don't necessarily need to create a model or have a model to use the software. Additionally, we also have battery model examples, and we're starting to build up that library. Offer, like when somebody is trying to emulate a battery, for example, we have a bunch of examples of 18650 cells, but at the end of the day, the user could also simply load their own battery model with those 3 parameters, and those 3 parameters consists basically, it's a CSV file. So
yeah, I'm trying to pull it up now to show people. Yeah, I don't know if you can see that or not. Can you guys see this? Because basically this is like the battery model file so it's very simple, very straightforward.
Exactly. So this model, right, consists of the state of charge, the open circuit voltage, and the internal resistance. So if it doesn't really matter, how this was obtained. For example, if you're using MATLAB to do some simulation of a battery model, and you want to load that battery model into our emulator to test your electronics, as long as the battery model consists of those 3 columns of information, we read that model into our software. Hopefully that answered the question.
Okay, good. The next question is, can you use a virtual battery to test your test routines, to try them before connecting to a real battery?
So this goes back, so virtual, so means,
Yeah.
any model, it's very almost related to the same exact question, which is basically the model you don't have to discharge a battery in order to use our emulator, an actual battery. If you have it, the content of the model containing the open circuit voltage and state of charge and the series resistance, we could just emulate it. So for example, if you just have like 10 points of from 100% all the way down to 0, and you put in those parameters of state of charge, and then you also put the parameters for open circuit voltage and internal resistance, we simply could just simulate that. So a good example of that, sometimes manufacturers don't necessarily give models as a file, but maybe they give a characteristic of the series resistance, the open circuit voltage, and the state of charge in a graph. You could simply pick some points in that graph, put it into a CSV file, and then just simply emulate it.
Okay, sounds good. The next question is, what is the difference between the N6783A BAT versus the N6781A?
Sure. So my favorite topic. So the N6783 is simply intended for a very basic performance battery to discharge a battery, for example. It does not have any series resistance capability, whereas the N6781 has series resistance capability. And like Alan mentioned, the importance of the measurement analysis as we're collecting this information of voltage and current consumption of a device, for example, as we're emulating a battery, the voltage and current measurement needs to be simultaneously measured, and it has to have very good dynamic capability on the measurement, whereas the N6783 does not have that. Okay.
Okay, so the 83, would it be fair to say, is a subset of capabilities?
That's not even a fair statement.
Yeah.
It's a very mediocre performance. It's only for those folks.
It's not supported.
It's not supported, exactly. Thank you, Alex.
Yeah, let's just leave it at that.
Okay, let's see. The next question is, how accurate is the emulator?
So it's all the emulation of our model is simply all derived based on voltage and current programming accuracy of our products. So depending on the the accuracy of the product that you're being used. So for example, you know, the N6781 that Alan was using, you know, it has the best in class of performance of accuracy from programming and also measurement. Our measurement system, give you an example, it's equivalent to 24-bit measurement system. So it's, in a bluntly saying, it's very accurate, okay? In terms of accuracy of voltage, I think our offset is like 0.02%. So that gives you an idea of the type of accuracies that we have, having an a 20 plus bit measurement system.
But it depends, of course, on the equipment, as Paul said too, right? Yeah, I mean, each one is different. Yeah.
Okay.
But even so, even at the, if you look at, for example, the RPS supplies, they have extremely good measurement capabilities for something that measuring such high power. They're very accurate, also extremely accurate for their class. So you can actually develop pretty accurate battery models for in any level of voltage and current you want to look at, really.
Okay, sounds good. The next question is does the N6705C, for example, include thermocouple input to monitor a thermal safety cutoff?
That's a great question. So,
yeah, it is.
So the our N6705 is basically just a power source. Okay, we do have products like our DAQ product line that could be used to measure and monitor temperatures of cells. And the nice thing about that is that our software runs on BenchView platform. So if a user would want to monitor the temperature of the battery, they would purchase the DAQ product, which has many channels to measure temperature with a variety of different thermocouple types that they could connect to their battery, right? And as they're running the test of our, for example, battery cycling, for example, they could, perform the test with our software and monitor the temperature. Okay. In a very near future, we are enhancing the software to integrate all that capability built into the application to make it very user-friendly to the user, but they still have to purchase the DAQ, just to be very clear.
Okay. That's all of the questions in the chat. If any of our guests would like to add additional questions to the chat, we'll monitor it here for a few minutes. And then you can also, I believe you would see a grayed out microphone that you can click on and it'll turn green. And then you'd be able to ask your question live through audio as well. So feel free to do that.
Yeah, so maybe just let me get through the last little bit here. So kind of a review. So we have the software is BV9210B for 4 instruments or 9211B for a single instrument. These are links if you want to get more information. Again, these are all the different products or the 4, I guess, key products that are supported by the software. Again, you can control up to 4 instruments. So that's pretty nice with the 4 multiple instrument version. So again, we can control lots of different power levels. I think it was also mentioned in those initial slides, but we also have, by the way, this is a little unrelated, but it is somewhat related. There is a new power handbook available as well. You can download it. It's PDF. It's about 146 pages. There's a link here if you want to go and download it, but it's got a lot of general stuff on power. It does have a section on batteries as well, but there's a lot of other stuff in it. So it's actually not a bad reference source if you want to just get that. And then it's pretty straightforward, pretty easy to download. And also, I wanted to also mention that we also have this All About Power webinar series that actually I've been running for a while. We've done the first 2, but all these, of course, are available on demand. So if you have an interest in this or any of these, you can sign up. There's a registration URL below. You look under Test and Measurement Bench Essentials, and you can sign up. And the next one that we're going to be doing in a couple of weeks is Practical Power Sourcing and Measurement Considerations. But again, these are also all recorded and available at least for up to a year on demand. So if you're curious about some of the other ones, you can sign up and then actually listen to any of them on demand if you don't want to listen to the live session. But yeah, so we have this available as well. And there will be actually another session coming up on battery and power management, which will probably go into some of the stuff we talked about here, maybe in a little more detail. I haven't yet exactly figured out what I'm going to talk about in that, but it'll be similar to what we talked about today, but maybe a little more detail on some other things as well. And I think that's all the slides I have right now. Yeah, so I don't know if there's any other questions on the software or anything else that we talked about.
Yeah, let's see, watching for any other customers. And before too many people leave, I just wanted to reiterate that we are recording this, so that recording link will be available for yourselves or others who couldn't attend. Same with the slides, we'll get the slides to you as well. And I think Paul had mentioned a couple other questions. Does Keysight offer battery models to use?
Oops, I was muted. So, so when we are building up a library of battery chemistries, as we are introducing the software, we are building up this library. So Alan just pulled up some examples of a variety of different batteries, and we're building up this library. So the answer is yes. So if, for example, if you're using an 18650 cell in your design, and you don't have a model of it, or you want to use a 18650 cell in your design, and you could just simply emulate this a battery using our own models. But I want to make it very clear that the models of this library have been developed by connected to a actual physical battery at a specific condition. So the condition during the creation of this model is very critical to the model being generated, simply because the battery characteristics would look different if the current condition that's being consumed by the device under test is different. So I want to highlight that importance, and that's why some folks, for example, some companies out there, they provide battery models, but they don't necessarily tell you the condition of the test, and so therefore you think that it's okay to be using that battery model in your application, but you may be misleaded, put it that way.
Okay, and then let's see, can you use the software as a virtual demo without being connected to the instrument?
Oh yeah, that's yet another great, especially with everybody with COVID working from home still and not having access to an actual hardware instrumentation. Our software, the BenchView platform, has a mode that you could simply enter into a demo mode, and then the user could launch the application that they want to launch in this demo mode. And it's basically then you're connected to a virtual PC, and simply you could use this functionality to maybe show your team the value of the software. So that's another way for the folks on the phone to be able to play around with the software and not having an actual hardware to connect to.
Yeah, maybe Paul, we should mention that you can download the software and try it on a trial basis for free, obviously too. So that's another option if you just want to try it, play around with it, either in demo mode, or if you have a supported instrument, obviously to try it with, you could use it that way too.
Yeah, and the trial license is good for 30 days. And then most of our software these days too, you can either buy a perpetual copy that you can use forever, or you could buy time-based licenses, you know, for 6 or 12 or 18 months,
Yeah.
whatever. There is another question in the chat. Assuming this software works on the 21700 cell as well.
So again, we don't necessarily care what type of battery you connect to us, as long as the battery's ratings are within the product's rating. For example, the N6781 has a maximum voltage of 20 volts. So as long as you're within the constraints of the hardware, we could test any battery, any chemistry, doesn't matter.
Right.
Okay. Sounds good. That's all the chat questions I see. Anybody that wants to unmute and ask a live question?
We're about the top of the hour. Yeah.
Oh, top of the hour too. Yeah. Okay. Well, we very much appreciate everyone attending our webinar today. Again, we'll have slides and recording available. When you close out, you'll be presented with an evaluation form that you can, you know, ask further questions or request a demonstration or any further dialogue. And yeah, once again, we thank our business partner Newark on this event as well. And I guess with that, Leslie, we'll go ahead and close this out, and everyone have a great day today.
Sounds good. Thank you so much. And thanks, Alan and Paul.
Thanks. Yeah.
All right.
Thank you.
Have a great one. Bye-bye.
Bye.